what we're going to do is, like I said, the time series analysis is chopped up into 3 pieces. And this lecture is about the introduction of the time series process as a discrete time random function that is often stationary, but it doesn't have to be stationary actually, but that we will show later in the later parts of this lecture on time series analysis. So let's move on. And so what is a time series? Well, this is an example of a time series. And you can see it is a realization of a random function, and there are only values at discrete time steps. In this case, every day there is one particular value. So a time series is defined as a stationary random function in time that is only looked at regular time intervals. Yeah? So the domain is time, the domain type is discrete, and it can be both continuously or discretely valued, but usually it's continuously valued. Often it's seen as a stationary random function, so if there's a trend or heteroscedasticity, such that the variance changes in time, or there's periodicity in it, often what they do is they first fit a trend function to it, either a periodic trend function or a linear trend function, and then subtract that from the time series, and then the remainder is assumed to be a stationary random function in time. And that is then modeled by time series models. So we are looking at a time series, at a random function, a discrete time random function that is usually shown as z with a subscript t, which is the time instance, and that's actually the value of the random function only considered at discrete time step of equal size delta tau. Yeah. And then t can be 0, 1, 2, 3. And if you generalize that in time series notation, that is z0, z sub 1, z sub 2, and so on. So these are discrete time steps. That's how we are looking at this. Now the seminal reference is how to analyze these type of random functions or time series is Box and Jenkins. Time series analysis, forecasting and control. This book appeared first in 1976, and it has been the basis of much research on how to analyze these time series and use them for use these analysis for all kinds of purposes. Actually, Box and Jenkins are not hydrologists. They're coming from economics and actually econometrics, and it was originally used to analyze the stock exchange value, so the values of stocks to understand why they vary in time. But actually soon after that it was already used to model stochastic modeling for instance, discharge or groundwater time series. And the modeling is often also then called a synonym for time series modeling. Discrete time series modeling is often also called Box and Jenkins modeling. So what is the goal of time series modeling? Why do we want to understand the statistical structure of underlying structure of these discrete time random functions? Well, the first one is to characterize them. So is there any trend, for instance, in my discharge data? Are there any drivers that explain its variability? Maybe that's the discharge can be related to El Nino southern oscillation or the North Atlantic oscillation. Or are there any interventions that can be seen? Is the increase in pumping rate of this drinking water station impacting the groundwater levels in the nearby nature area? Or do I see that, can I see that discharge has changed due to dam building upstream? So these are interventions that can be analyzed by looking only at the time series and statistically analyzing them. A second reason is to do data infilling. Sometimes you have observations and you have holes in them, and often if data are to be analyzed maybe by third parties, it may be one way of doing the infilling is trying to interpolate them, looking at the statistical structure of the data, and then using a statistical model to interpolate. Well, you can also extrapolate with the same model, but then it's called forecasting. Yeah? Suppose that we have the discharge of today and yesterday and the day before. We may want to predict what the discharge of the river is going to be in the next few days, without having a complicated hydrological model fitted to the data. And then finally, this is more for, sorry? Yes, it's a question? I heard there was a question or not? No? Okay, then I'll continue. And then the fourth reason is simulation. I often call that statistical extrapolation. Suppose that you have 2 years of observations of discharge, or 3 or 4 or 5 years, but you want to have a long enough sample to design your of discharge to design your dam or dikes from. Then if you are able to analyze what the statistical structure is of the time series and build a model from that, you can use that to simulate many equally likely realizations of that time series that all have the correct statistical properties. And then by de facto statistically extrapolating the time series so that you are able to analyze under the uncertainty to basically do design while taking account of the uncertainty of the underlying process. So those are 4 main reasons why we want to do time series models. Now, just looking at some basic statistics, and these are borrowed from the random function theory, and assuming that we have a stationary, or actually what I should say, a wide sense stationary random function, then the expected value is just given by the symbol mu. The variance is given again by the symbol sigma squared. The covariance between Zn plus k and Z is often denoted by the capital C, with lag is K is the lag distance. So the actual lag distance in time units is K time steps. So the length in time is then multiplying K with the fixed time step of delta tau. And of course, if we take the covariance and we divide it by the variance, we get the correlation function. And this, because this is the correlation between Z and itself, K time step removed, this is called the autocorrelation. So we can have an autocorrelation function, which gives me the correlation between Z and itself, K time steps removed. But we can also have the cross-correlation function, which is when we have 2 variables. This can, for instance, be the time series of discharge with 2 different time steps, and this may be the correlation between precipitation at n and the discharge k time steps further down. Yeah. So we can also have the cross-correlation function. So a time series can be defined by its basic statistics, a wide sense stationary random function, discrete time random function, by its mean, its variance, well, this is mean plus or minus the standard deviation, and the correlation, the autocorrelation function. Yeah, with these 3 statistics, if we assume this thing to be Gaussian and wide sense stationary, we can fully define that random function. Now, of course, these are basic statistics given like this, but suppose that we have the same mean and standard deviation, but a different autocorrelation function. You can see it looks like this. Yeah. So you see that the correlation length is much larger than the previous one. Yeah. Here the correlation length is say 10 time steps, and then the random variables at these at more than 10 time steps apart are no longer correlated. This is not the case here. Here you see correlation is up to more than 20 time steps removed, and you can see that the excursions below and above the mean are much longer, therefore. Yeah. Now, if we do predictions, yeah, so forecasting ahead in time, or interpolations, we do the data infilling, we have to have a model that describes the underlying statistical structure of the observed time series. And because it involves time, such a model should distinguish between past and future. They are different. So they take account of what is called the arrow of time. Yeah. And actually, that's the second law of thermodynamics. So, things only move, entropy only increases if you don't put any energy in a closed system. Entropy increases with time, right? But not the other way around. So this is also here the case, and that means also that if you have, for instance, two variables, the cross correlation between time 0 of one variable and time 2 of the other variable is not the same as the other way around. So there is a causality in there. So our model has to have that arrow of time and causality in it. So those are the type of models. And to do that, we use so-called recursive models, which means that the model predicts a value today as a function of what was found yesterday or the day before. Yeah. That's where most Box-Jenkins models work for. And before we go and introduce the main classes of Box-Jenkins type of models, we're going to define some specific Box and Jenkins algebra. It's interesting to learn that, and the reason is because it allows you to write quite extensive models with a very easy shorthand notation. And if you write, or if you read papers about time series models, you have to understand this shorthand notation. So this is why I'm going to introduce that to you first. So two important operators that are used in Box and Jenkins modeling is the so-called backward shift operator and the backward difference operator. The backward shift operator says that if we put it before a certain variable zt, then we mean that b times zt is equal to zt minus 1. Yeah. So it shifts. So multiplying z with b then means in this algebra looking at z one time step back, or z I should say, one time step back. Yeah. And then you have the backward difference operator. That's the nabla. So that's basically it's called the nabla operator. So nabla zt is zt minus 1. Yeah, it's the difference operator and backward difference. And actually, you can easily see that because zt minus 1 is b times zt, then we can substitute b times zt here, and then factorize that thing, and we get 1 minus b zt. So nabla zt is the same as 1 minus b zt. These things are interchangeable. And by the way, why would you want to do the difference? Well, the reason you want to have a difference operator is that sometimes if you have a linear trend, for instance, in your time series, you can do the time series analysis on the difference operator of z. So instead of analyzing Z with a time series model, we're analyzing nabla Z. And then because if you have a linear trend, if you subtract, and you have a fixed time step, you subtract the Z minus ZT minus 1, you basically, you effectively remove this linear trend from the time series. So that's one way of making a time series stationary. Now, just some Box-Jenkins algebra. For instance, if we have B squared ZT, that's the same as B times B ZT. We can replace B times ZT with ZT minus 1. And B ZT minus 1 is, of course, ZT minus 2. Yeah. So in general, B to the power of n ZT is ZT minus n. Yeah. So this is a generalization of the backward operator. And also the nabla operator can be squared, or so the squared value of the nabla operator is nabla times nabla ZT, and nabla ZT is ZT minus 1. Then we can get rid of the brackets, so we get nabla ZT minus nabla ZT minus 1. This guy here is this, and this one here is this. Get rid of the brackets and we get ZT minus 2 times ZT minus 1 plus ZT minus 2. Yeah. So we can then get the B's in again. Yeah. ZT minus 1 is B times ZT and ZT minus 2 is B squared ZT. And then we can factorize this thing again, taking ZT out of the brackets, and we end up with 1 minus 2b plus b squared zt, and we can further factorize this as 1 minus b squared. So in general, nabla to the power of n is 1 minus b to the power of n, can be replaced. Yeah, so these things are interchangeable. So this is your Box and Jenkins algebra. We come back to this later when we introduce the different types of time series models that we have. Now let's move to these so-called time series models. What are they look? How are they built? What do they look like? Well, the basic time series model is built on white noise. This is an example of white noise. If you look at the correlation function of white noise, it has a correlation of 1 for leg 0, and it has a correlation of 0 everywhere else. I want to remark that this is discrete time white noise. This is something else than continuous white noise altogether, because continuous white noise, as we saw before, has some ugly properties in the sense that its variance effectively is infinite. And it's of infinite variation. That is not the case for discrete white noise. It has a finite variance and a given mean. And if you have standard Gaussian, and it's Gaussian distributed. A standard Gaussian discrete time white noise process, if it's a standard Gaussian, of course, the mean is 0 and the standard deviation is equal to 1. Yeah? So these are two other realizations of the same discrete time white noise process. Yeah. Again, the correlation function has a value of 1 for leg 0 and 0 everywhere else. And these are the statistics of discrete time standard Gaussian white noise. Now you can easily generate that in R. You define a vector A, which is defined using the R norm function. So it generates standard Gaussian. If you don't give it any other parameters, it generates standard Gaussian white noise. And this is a length 100. So if you plot it, you get 100 time steps of discrete time white noise. Now, what's the basic idea about time series modeling? So the models have some dependency in time, because we already saw, if we went back to our time series, that there is dependency in time. So that has to be somehow generated by our models. And there are different types, so-called autoregressive models of different order, so-called moving average models, and a combination of both, so-called autoregressive moving average models of different order. The basic idea is that any of those models is nothing more than a linear combination of white noise. Yeah? So we generate a time series of white noise, and we construct a certain linear combination of these white noises, and that generates a dependency in time. So we're starting with the most elementary process, and this is called a first order autoregressive process. And the model to simulate it is a so-called AR1 model, which describes an AR1 process. The AR1 process is simple. Taking, you define a certain initial value Z0, it can be also 0 if you want to, and then Z at the next time step is phi1 times Z of the previous time step plus some standard white noise. Yeah. Now the only parameter that we have here is phi1. That's the first order autoregressive parameter, as it's called. And this phi1 actually, we can prove, we do that later, that its value is equal to the lag 1 correlation. Of course, this time series, you may want to simulate a time series that has a mean different from 0 and a variance different from 1. So what you typically do is you simulate a series like this, then you add your mean to it, and then you multiply, you first multiply everything with the variance of with the standard deviation of Z, and then you add the mean, and then what you get is an autoregressive order 1 process of the correct mean and the correct variance. Now let's throw some Box-Jenkins algebra at this, right? So we take this guy here, Zt is phi1 times Zt minus 1 plus At. We can replace Zt minus 1 by B times Zt. You can see that here. Then we can move this one to the left side of the equality. So we get 1 minus V1b Zt is equal to At. And if we define this function, which is a capital phi as a function of b, as 1 minus phi 1b, it's a polynomial in b, then this is the shorthand notation of this specific model. Now we can easily simulate this again in R. We first define vector, we first define the initial value of Z. Well, it's going to be 0, as you can see here. Then we say A is the, we define a vector of length 100 of standard normal deviates, as you can see here. And then in a loop for I is 2 to 100, we say Zi, and here phi1 is 0.8, is Z 0.8 times Zi minus 1 plus AI. Yeah. So now we fill in Z between 2 and 100 with these values. As you can see, the initial Z is equal to 0. And then if we plot it, we get this realization of an AR1 process. So in the homework that you need to do, you're asked to also simulate these processes. You can easily check it in R and do it yourself. Now this is a first order autoregressive process. We can also increase the order. So here you see a second order autoregressive process, or a AR2 process. And because we have two autoregressive terms. So Z at the current time not only depends on the Z of the previous time, but also on Z of 2 times back. Yeah, and the whole thing becomes stochastic because we keep on adding every time step this random noise. Yeah. And here you have 2 parameters. Or actually, if we just subtract the mean and the variance and we estimate it from the data, we actually effectively have 4 parameters. We have the mean, we have the variance, and we have these phi1 and phi2 parameters. So it's a 4-parameter model. Yeah. So we can release the same, we can actually throw the same box in Jenkins notation at it. ZT is phi1 times B ZT plus phi2 times B squared ZT. Take these two, take them to the other side, factorize the thing so that ZT is outside the brackets. And then if we define a new polynomial, yeah, phi, capital Phi as function of B is now defined as a second order polynomial. We can write it like such. Yeah? So this is the same shorthand notation for a higher order autoregressive process. Now if we generalize this even further, so we have an autoregressive process of order P. So we have P autoregressive term plus some white noise. So now ZT depends on P on the Z, P time steps back. You can see this model becomes richer and richer, as you can see. We have P plus 2 parameters in this case. And again, if we define the polynomial, if we define capital Phi B as a polynomial in the backward shift operators, a polynomial of order P, this is again a shorthand notation. So you can see no matter what the value of P is, we have the same way of writing, shorthand at least, this autoregressive order process. So you, in the literature, you will see, okay, we have, they'll give this notation here and they also give you the order P, and you're able to write it, you extend it and write it like such. So this is an autoregressive process. Then let's move to the other type of process. This is a so-called moving average process. Now, a moving average process is actually consists of a moving average of the noise terms only. So Z at T depends on the noise at the same time, but also on the noise of the previous time step. Yeah. And this is a so-called moving average parameter, theta 1. This thing has therefore 3 parameters, theta 1 plus the mean and the variance. Yeah? So again, if we want to simulate it, we simulate first this. Suppose that we have the autocorrelation function from the data, then we choose theta such that it reproduces the autocorrelation function. Simulate the time series like this, and then maybe if that's needed, multiply times the standard deviation and add the mean to get a moving average process of the correct mean and variance. Now we can also do the box Jenkins notation here. ZT is AT minus theta 1 AT minus 1. This thing here is replaced by B times AT as you can see. Then we can factorize it and then we define a polynomial. ZT is capital theta B times the noise AT. And of course, we can also bring this to the other side. Sometimes it's written like this. Yeah? Now this can easily be simulated again with R. So we create a vector of length 100 of standard Gaussian noise. We take the initial value Z equal to 0, and then we loop over 2, Z is 2 to 100, and then Zi is the noise at I minus the moving average parameter times the noise at the previous time step. And we plot it, and here we are again. Yeah, easy. Now this is the way to, first of all, you see these models are unidirectional. So ZT depends on what happens at the previous time step, either the noise in the previous time step or the value of Z itself in the previous time step, and that also creates dependency. And you can see it like this. In an autoregressive process, ZT, the dependency is because part of ZT depends on the value of Z at the previous time step. For the moving average process, the dependency arises because they both have the same value of the noise, AT minus 1 in this case, in common. Yeah. So there's a communality between ZT and ZT minus 1. Yeah? So that creates temporal dependency. Now, of course, this is a moving average process. We go through this quite quickly. We have two parameters. We can again work this out, but now it looks the same, but we have now a polynomial, a so-called moving average polynomial of theta in of order 2. And of course, again, we can do it in general of order Q. So this is a moving average process of order Q. And then we can write it actually shorthand the same way, but now the polynomial theta as a function of B is a polynomial of B in of order Q. Yeah. Now what we can finally do as a final time step, yeah, is a so-called general linearized process, actually a general linear discrete time Gaussian distributed wide sense stationary random process. In its most generality, it's the so-called ARMA PQ process. So we have P autoregressive terms, and we add to that M Q moving average terms. Yeah. And if we define the polynomials like this, phi as a function of B, or theta as a function of B, polynomial of the order P or polynomial of the order Q, a shorthand notation of this ARMA PQ process looks like this. Now, we already saw that it's easy actually to get the mean and the correct variance. So if we want to apply this to a real time series, what we typically do is calculate the mean, subtract the mean. Hopefully there's no trend. If there's a trend, you subtract the trend. You calculate the variance, you divide everything by the standard deviation then, and once you have the variance calculated, and then on the remaining residuals, you're then applying this time series model. And once you have simulated a series or forecasted the series, you can then add the mean and the variance again. Yeah. But what if these residuals are non-Gaussian? Then you're in trouble, because we assume that to be standard Gaussian. So if they are non-Gaussian, what they typically do then is a so-called box-Cox transform. This is the transformation that is often used in time series modeling, where they optimize lambda 1 and lambda 2 such that Z is as Gaussian as possible. Yeah. You can do that by actually you can do that by plotting, do a quantile against quantile map. One is a quantile of the Gaussian distribution, a standard Gaussian distribution, and the other one is the quantiles of the original distribution of Z. And then you do this transform, this box-Cox transform, and then you optimize lambda 1 and lambda 2 such that on the quantile map they become aligned on a not a one-to-one line, but on a straight line. If you have done that, you made sure that this is a Gaussian transform.